Hello, my name is William Munizzi. I'm a fourth-year PhD student at Arizona State University, where I work as part of the Cosmology Initiative under my advisor, Dr. Cynthia Keeler. The focus of my research surrounds various mathematical models for quantum systems and their characteristic properties. Today, I'd like to talk about the research surrounding the paper, An Entropic Lens on Stabilizer States, a recent project completed by myself, Dr. Keeler, and Dr. Jason Pollock. What we propose in this paper is a new method for analyzing and characterizing stabilizer quantum states and their properties. But before I begin, I will need to introduce some background on quantum information theory and quantum computing. So what exactly do we mean by quantum information? What is a qubit anyway? And why should we care so much about stabilizer states? Quantum information theory is the study of information characterization and transmission at the quantum mechanical level. When we examine the world at a macroscopic scale, what we refer to as classical physics, properties of physical systems appear as on a continuum and can be measured consistently and with absolute certainty. This is not so at the quantum level. Quantum mechanics places various restrictions on physical systems and what we, as observers, can measure when analyzing those systems. This phenomenon manifests as an inherent uncertainty when making measurements on a quantum system. Any hope of quantum computing relies on the ability to create and manipulate quantum mechanical systems consistently and accurately. So how can we accomplish that? Well, let's start from the beginning. The qubit, or quantum bit, is a physical system subject to the laws of quantum mechanics that can be observed or measured in one of two distinct states. This could be some resonant magnetic cavity, a superconducting circuit, trapped ion, or even a photon. The physical realizations are numerous, but from a computational standpoint, the qubit is analogous to the standard bit in classical computing, which is typically represented by a 1 or a 0. We can string together some sequence of zeros and ones to form a message. Similarly, we can string together a collection of qubits to form some composite quantum state. A collection of qubits is known as a quantum register. Unlike standard bits in classical computing, prior to being measured, the qubit can exist in a superposition of 0 and 1. This purely quantum behavior leads to some peculiar effects that simultaneously makes quantum computing so powerful and yet tricky to navigate. In classical computing, strings of bits are altered with logic gates. Qubits, similarly, are modified with quantum logic gates. These gates can perform an array of functions, each manipulating a system of qubits in some way that is consistent with quantum mechanics. These manipulations can include flipping a qubit on or off, rotating a qubit into an alternative measurement representation, and much more. A sequence of quantum gates is known as a quantum circuit. In quantum circuit diagrams, the initial state is represented by a collection of qubits to the left. Wires extending to the right from each qubit indicate the evolution of that particular qubit in time. Quantum logic gates occurring along the wire for a particular qubit or set of qubits act on those qubits at that instant in time. Different sets of quantum gates emit special properties that make them desirable as a point of study. One such group of operations, known as the Clifford group, is unique in its ability to be efficiently simulated on a classical computer. This is, of course, of great interest as we explore the waters of quantum computation. The Clifford group can be built of only 3 quantum gates. They are the Hadamard gate, the phase gate, and the C0 gate. The matrix representation of each gate is given here. But what exactly do these gates do? The Hadamard and phase gates are what we refer to as single qubit gates, meaning they only affect one qubit at a time in a physical system. The Hadamard gate transforms a state from a vector representation that can be measured with certainty in one basis to an alternative vector representation in a different measurement basis. Meanwhile, the phase gate introduces a relative imaginary phase between the basis states of a mixed state. On the other hand, the C0 gate, or controlled NOT gate, is what is known as a multi-qubit gate. The C0 gate takes in 2 qubits, interprets the first qubit, the control bit, and flips the second qubit, the target bit, if and only if the first qubit is on. Otherwise, the system is left unchanged. Even with this small collection of gates, we can already observe the strange consequences of quantum mechanics. As we know, a single qubit can exist in a simultaneous superposition of measurement states. So what happens if the C0 gate cannot tell with certainty if the control bit is on or off? It turns out this is exactly one way of creating entanglement. One major goal in quantum information science is to organize and classify various quantum systems based on their constituent properties. On the last slide, I introduced the Clifford group. If I were to consider quantum circuits constructed from only those Clifford gates, I would only be able to build what are known as stabilizer circuits. These circuits hold a special prominence in the field of quantum error correction. The torque code here is one famous example of a stabilizer code, but that is a topic for another day. What makes these stabilizer circuits interesting for our purposes is that they limit the set of quantum states one can reach under circuit evolution. In other words, the quantum gates of the Clifford group do not form a sufficient set of gates to perform universal computation. For this reason, if we initialize our system in a particular quantum state and evolve that state through a stabilizer circuit, we can only ever reach a discrete and finite set of new quantum states. Another meaningful property is entanglement entropy, a quantitative description of how information is stored in a quantum system. Entanglement entropy affords us as physicists another signature that can be used to classify quantum states. As it turns out, states with certain entanglement structure can correspond to states with additional special properties. For example, well-behaved states in quantum gravity. The question then becomes, what information can we learn about a system by examining some limited set of properties, and how can we use that information to infer further properties of the system? Additionally, what novel methods can we concoct to extract the meaningful information from a system in a clear and intuitive way? The set of stabilizer states can be organized into a visualization known as a reachability graph or reachability diagram. These graphs encode the full information regarding state evolution under action of the Clifford group. In these diagrams, vertices represent different quantum states, and edges represent the particular logic gate that moves us between states. The color of each vertex denotes the amount of entanglement present in that particular quantum state. Now consider the reachability graph of a single qubit. The single qubit Clifford group consists of all combinations of the Hadamard and phase gates. All vertices in this graph have the same color. This is because there is no such way for a qubit to be entangled with itself. At least 2 qubits are required for entanglement. As we can see, this graph decomposes into 2 substructures. One, a collection of states related by the phase gate operation, and the other, a collection of states connected via a Hadamard operation. As you can see, this graph provides a visual map to navigate the space of single qubit stabilizer states. If we want to know which sequence of gates or circuit will take us from an initial starting state to some desired end state, we need only trace the corresponding path along this graph. From a mathematical standpoint, this representation offers a new set of tools to study these complicated physical systems. What happens if we do this for 2 qubits? Here is a reachability diagram for a system of 2 qubits. Notice the addition of a new quantum gate, the 2-qubit C0 gate, indicated by the pink edges. We can also notice the arrival of a new vertex color, red. Since we have 2 qubits, we now have the possibility for entanglement to occur. For a system of 2 qubits, there are 60 possible stabilizer states we can reach. There are also 2 possible entanglement structures available, those being 2 unentangled qubits and 2 entangled qubits. The 2 entangled qubits form what is known as an EPR pair. While this diagram contains all of the information regarding the interaction of 2-qubit stabilizer states and their entanglement entropies, the image itself can be difficult to parse. Since the number of states and gates scales exponentially with qubit number, the problem will only get worse when we move to larger and larger systems. How can we then continue to extract the desired information from these reachability graphs at higher qubit number? It turns out, many of the relevant properties of these quantum systems are accessible even when only examining subgraphs of the full reachability graph. For example, if I only wish to examine how a set of 2-qubit stabilizer states behaves under action of the Hadamard gate, I get this graph. That is to say, I have removed all edges corresponding to C0 and phase gates, in order to focus solely on the effects of the Hadamard operation. As you may recall, the Hadamard gate is a single qubit operation. Therefore, we can consider its action on qubit 1 or qubit 2 of this system, indicated by the solid green and dashed green lines respectively. We refer to these graphs as restricted graphs and analyze their structure to make conclusions about our system. In this restricted graph representation, we can better examine features of interest. For example, it is clear from the diagram that the Hadamard gate does not alter the entanglement structure. All blue vertices group with other blue vertices, and red vertices with red. Furthermore, the vertices arrange into boxes, with the exception of the 4 unique states in the bottom right. These boxes illustrate symmetries of the states up to different basis representations. Those states in the bottom right have an additional level of symmetry, causing their boxes to collapse into the degenerate pairs you see. This structure validates our earlier remark about the Hadamard gate initiating a change of basis. Let's consider another example of a 2-qubit restricted graph. Here I have removed only the C0 gates, the pink edges, from the original complete 2-qubit graph we discussed earlier. What do we notice about this restricted graph? Upon removing edges corresponding to the C0 gates, the graph completely separates into 2 pieces, one containing all of the unentangled states, the blue vertices, and one containing all of the entangled states, the red vertices. We observe then that only the C0 gate is capable of altering a state's entanglement entropy. Additionally, if we look closely, we can observe the structures on the left as different copies of the 1-qubit reachability graph, attached via different Hadamard gates. What if instead we restrict to only Hadamard and C0 gates in our 2-qubit system? We observe a different separation in the restricted graph structure, this time with 2 subgraphs that are separated by a phase gate. This type of restricted graph will play a special role in our analysis, as it turns out, given the properties of the Hadamard and C0 gates, all non-trivial entanglement dynamics can be captured in restricted graphs such as this one. So what happens when we extend to larger qubit systems? We can perform the same analysis at 3 qubits by generating the full reachability graph, then removing all edges that are not representing a Hadamard or C0 gate on the first 2 qubits. While we are choosing to preference qubits 1 and 2 in this demonstration, the analysis is sufficiently general for any 2 qubits selected from a multi-qubit system. Upon building the restricted graphs, we witness the arrival of 2 larger and more complicated structures, one containing 144 vertices, and the other 288 vertices. The vertex count of each subgraph is indicated above the structure. As we can see, at 3 qubits, there are 5 different entropic structures, indicated again by vertex color. It should be noted that this particular image does not contain all 3 qubit stabilizer states. In fact, there are 1,080 of them, but rather it shows one copy of each unique subgraph structure appearing at 3 qubits. In the full restricted graph, we find 6 copies of the subgraphs G24 and G36, one for each way we can add a new qubit to our 2-qubit system. We find 3 copies of G144 and a single copy of G288. When we move to 4 qubits, we get yet another restricted graph structure. This new subgraph contains 1,152 vertices and 2,304 edges. This new structure also comes in 2 varieties at 4 qubits. One variety has 4 different vertex colorings, like that shown here, and the other has 2 different vertex colorings. So does this trend continue as we extend to larger and larger systems of qubits? That is to say, as we continue to add qubits to our system, do we observe the arrival of newer, larger subgraph structures? Perhaps surprisingly, the answer is no. The 5 restricted graph structures I have shown you thus far are in fact the only structures that arise in graphs restricted to Hadamard and C0 gates acting on 2 qubits in a multi-qubit system. How can we be so sure of this without explicitly checking to arbitrary qubit number? Recall a moment ago, I mentioned this graph contains 2,304 edges. Each edge corresponds to one of the 4 quantum gates listed to the right of the image. As it turns out, there are exactly 2,304 unique operations that can be built out of combinations of these 4 gates, and each unique constructible path through this graph corresponds to one of those unique combinations. So now that we have established all possible subgraph structures built of the Hadamard and C0 gates on 2 qubits, what additional information can we extract from these diagrams? Well, for one, we can now employ graph theory to study the set of stabilizer states. We could construct various paths, cycles, graph covers, and graph embeddings, each of which demonstrates some aspect of the underlying physics governing these states. These structures have allowed us to observe how higher qubit graphs are really just attached copies of structures appearing in lower qubit systems. Accordingly, larger structures can collapse down into smaller ones when certain quantum gates leave a particular state unchanged. Additionally, although we get no new subgraph structures beyond 4 qubits, we do find that the diversity of entanglement entropies among certain subgraphs continues to increase as we go to larger and larger qubit number. This means the number of different vertex colors increases on as we increase the number of qubits in our system. For example, the 144 vertex subgraph here had 3 different vertex colors at 3 qubits, but gains a new 4th possible coloring at 4 qubits. This pattern occurs on all subgraphs with 144 vertices or more. However, even this vertex coloring increase must terminate at some number, but just how many qubits are required to do so, and why is that number so special? This restricted graph analysis is not limited to stabilizer states. Rather, there are fundamental properties of the underlying Clifford group being displayed here. To the right is a restricted graph showing Hadamard and CNOT gates acting on the W state, a well-known quantum state that is explicitly not a stabilizer state when we move beyond 2 qubits. Even the largest and most complicated of the subgraphs I have shown you are really just intricate attachings of the fundamental building block shown to the left. Given the way this structure is assembled, there is maximally 10 different entanglement entropies present. This constrains the maximal number of entanglement entropies available for all stabilizer states, but just how big does that number ultimately get? How many different ways can stabilizer states become entangled, and what can this tell us about other classes of quantum states? Earlier, we discussed some introductory topics in quantum computing and quantum information. I presented the general structure of quantum systems as collections of qubits and described their evolution through a quantum circuit. We reviewed some formalism of the Clifford group, the way its elements act on quantum states, and the special class of states it can generate, the set of stabilizer states. We introduced the construction of reachability graphs, how they offer an illustrative representation of stabilizer states, and explored a new method for analyzing stabilizer states by selecting out restricted subgraphs and studying their properties. As we extended our analysis to higher and higher qubit number, we found some interesting results. Notably, the number of new subgraph structures does not increase beyond 4 qubits. Instead, the diversity of entanglement entropies among the different subgraphs increases, but even this must level off at some point. Further investigation into these graphs reveals a fundamental structure from which all other graphs can be built. The maximum entropic diversity of this block limits the number of entropic arrangements one can witness in stabilizer states. Finally, since this structure was established at the operator level, with no special preference of quantum state being acted on, one can continue to apply this analysis to any quantum system. In this way, one can gain a more general understanding of the state and entanglement dynamics under action of different quantum circuits. As a final remark, I would like to thank the people who made this research possible. First, I would like to thank my collaborators and co-authors, Dr. Keeler and Dr. Pollack. I would like to thank the IT from Qubit collaboration, the US Department of Energy, and the Heising-Simons Observational Signatures of Quantum Gravity collaboration for their financial support of Drs. Keeler and Pollack and myself. Finally, I would like to thank you for watching this video. It is always a rewarding opportunity to share one's discoveries and discuss physics with any and all interested individuals. If you liked this video and found it interesting, feel free to comment on this video or connect with me to learn more. And don't forget to check out our paper, An Entropic Lens on Stabilizer States, currently available on archive.org. Thank you.